Hi, I'm Jason. In this little demo, I want to show that there exists an undecidable language. My motivation today is to prove there exists an undecidable language. To do this, let's first get our terms straight. What's a decidable language and what's an undecidable language? Well, a decidable language is a language for which there exists some algorithm that for all inputs gives us the correct output. So with the terms we know from 376, let's write our definition out. A decidable language. So there's some Turing machine, right, that performs our algorithm, for which, or such that this Turing machine on all outputs X gives us the correct output. For all the inputs we could possibly think of. So in this case, all strings made of zeros and ones. Now, one thing to note is for a Turing machine to give us the correct output on all input strings, it must also halt. Can't just keep spinning forever. So note that this always halts. Great. And what do we know about Turing machines? Well, for one thing, we know that there are a countable number of them. One way we can get a sanity check on knowing this as a true fact is that Turing machines have a finite specification. There are a finite number of states and a finite number of rules moving between those states, or transition rules. So you can imagine a scheme in which we map these finite specifications to a natural number. And in fact, there are such schemes, but I just won't go into detail here. So let's make note of that there are a countable number of Turing machines. So this gives me a motivation to use a diagonal argument to find out if there are undecidable languages. Great. Let's try it out. With a countable number of Turing machines, just like in the case where we proved that the real numbers are uncountable, we can't map them on one-to-one with the natural numbers. Let's list all the Turing machines on one side. And to represent these Turing machines, let's list the input strings along the top. Right, these are input strings X. And to represent a Turing machine in this chart, we're going to say whether or not this input string, let's say 0, is included where this by this Turing machine, the language of the first Turing machine. So let's say that 1 is included, 2 is included, 4 is included, but 0 and 3 aren't. And this is how we're going to represent a language that is decided by this Turing machine. So there could be a Turing machine for which only the even numbers output yes, but the odds don't. The opposite could be true. Evens output no, but the odds say yes. Or maybe there's a Turing machine that simply says yes to all inputs. You get the idea that we can list all languages that these Turing machines are specifying or deciding. Now, let's look at this diagonal, just like in the original diagonal argument. And let's imagine a new language L that's defined to be different to each of these languages in each of these elements. So since the first Turing machine says no on input 0, this Turing machine will say yes. Since the second Turing machine says no on the first input x equals 1, we're going to let the output be yes to negate that. So what we've just done is constructed a language that we've defined to be different from all the languages contained in this chart, right? This chart up here. What does that mean? I've just created a language that isn't decidable by any of the Turing machines, even though I've listed all the Turing machines. Therefore, L is an undecidable language. So yay, I've done what I wanted to set out to do, prove there exists an undecidable language. But not only have I done that, I've done it using a diagonal argument. So I can say something even stronger, actually. Just like we know that the real numbers are uncountable, we know from this argument that I can create an uncountable number of undecidable languages. So there's a bizarre case here that if I were to pick out a language at random, I would actually expect it to be undecidable, for us to not be able to find an algorithm to decide that language, rather than for it to be decidable. Thank you.